we can go to the next section of this module, that is surface integral, and we find relate surface integral using Gauss divergence theorem. Now we can evaluate surface integral. You are given a surface in the 3 dimension whose projection can be taken to the xy, yz and zx plane, and evaluation of surface integral over sigma f of xy z ds can be evaluated using 3 formulas. The first one is the sigma is a surface with the equation z is equal to g of xy and r is a projection on the xy plane, and if g and h has continuous first partial derivatives on r and f of xy z is continuous on sigma, then integral over sigma f of xy z ds equal to double integral over r f of xy z can be substituted as g of xy. It is given into root of dou z by dou x whole square plus dou z by dou y whole square plus 1 dA. And if the given surface, the projection was taken on the xz plane, then y can be defined as g of xz, then integral over sigma f of xyz ds is given by double integral over r f of x, substitute for y as g of xz comma z into root of dou y by dou x whole square plus dou y by dou z whole square plus 1, since y is given as function of z. Similarly, if the projection was taken on the yz plane, then x is equal to g of yz. Therefore, integral of f of xyz ds equal to double integral over r f of, substitute for x as g of yz comma y z into root of dou x by dou y whole square plus dou x by dou z whole square plus 1 dA. Now we can apply this result to do some problems, and the same formula is written here 1, 2 and 3. The formula 1 is given when the surface is taken the projection to the xy plane, and equation 2 gives the projection of the surface taken on the xz plane, and equation 3 is the projection was taken on the yz plane. Consider a problem. Evaluate the surface integral. The surface integral double integral over sigma y square z square ds, where sigma is the part of the cone z is equal to root of x square plus y square that lies between the planes z is equal to 1 and z is equal to 2. Here the surface of the cone z is equal to root of x square plus y square, that is z is given as function of xy, that is g of xy, z is equal to g of xy, and our integration is integral over sigma y square z square ds. Since z is given as function of xy, you can use the formula equation 1 to evaluate the integral over sigma f of xyz ds, that is equal to double integral over r function of x y g of xy ds is square root of dou z by dou x whole square plus dou z by dou y whole square plus 1. Now comparing equation 1 with this integral, you can see f of xy z is equal to y square z square, where z is given as z is equal to square root of x square plus y square, which is a cone. The cone in the 3 dimension is given by z is equal to square root of x square plus y square. And given that the surface, the part of the surface of the cone that lies between the planes z is equal to 1 and z is equal to 2. Suppose this is x-axis, y-axis and z-axis. The plane z equal to 1 means this point is 0, 0, 1. A plane is cutting the cone through the point 0, 0, 1 and parallel to the xy plane, and the upper portion of the plane is z is equal to 2. Suppose this point is 0, 0, 2. That cone is cutting by the plane z is equal to 2. This passing through 0, 0, 2 and parallel to the xy plane. For the figure will be the part of the cone between z is equal to 1 and z is equal to 2. And we are using the formula 1. So we take the projection of the surface between z equal to 1 and z equal to 2 to the xy plane. This is xy plane. The projection of z is equal to 1 gives the circle x square plus y square equal to 1. The projection of the surface z equal to 2 gives on the xy plane the circle x square plus y square equal to 4. For the projection of the surface on the xy plane gives the annulus region between the circles x square plus y square equal to 1 and x square plus y square equal to 4. The region are defined here as the region between the circles x square plus y square equal to 1 and the circle x square plus y square is equal to 4. Now we can consider the integral. Then integral over sigma y square z square ds can be converted into double integral over r f of xy g of xy square root of dou z by dou whole square plus 1. That is double integral over sigma y square z square ds is equal to double integral over r y square into, you have given z is equal to square root of x square plus y square. Therefore, z square is equal to x square plus y square into square root of, we consider square root of dou z by dou x whole square plus dou z by dou y whole square plus 1. Dou z by dou x whole square plus dou z by dou y whole square plus 1 dA, where z is equal to square root of x square plus y square. Therefore, dou z by dou x is equal to 1 by 2 root of x square plus y square into 2x, and dou z by dou y is equal to similarly 1 by 2 root of x square plus y square into 2y. Therefore, square root of dou z by dou x whole square is x square divided by x square plus y square plus dou z by dou y whole square is y square divided by x square plus y square plus 1 equal to square root of x square plus y square divided by x square plus y square plus 1. That is square root of 1 plus 1 equal to root 2. Now substitute the value root of dou z by dou x whole square plus dou z by dou y whole square plus 1 in the integral, we get integral over r y square into x square plus y square into this value is root 2 dA. dA means dx dy. Now our region of integration is in the xy plane between the circles, that is between the annular region, that is between the circles x square plus y square equal to 1 and x square plus y square is equal to 4. Now we can convert Cartesian coordinate to polar coordinates by the substitution x is equal to r cos theta, y is equal to r sin theta, so that dx dy is equal to r dr d theta. If we consider a radial vector OQ, this radial vector intersect the first circle x square plus y square equal to 1 at the point P and x square plus y square equal to 4 at the point Q. And our required region is between the circles x square plus y square equal to 1 and x square plus y square is equal to 4. The radial vector r is varying from the inner circle to outer circle. Therefore, r is varying from 1 to 2 and theta is varying from. To describe the full region, the angle theta is the angle between the initial line and OQ. Then theta varies from 0 to 2 pi. Now we can convert this integral into double integral where y is equal to r sin theta for r square sin square theta, x equal to r cos theta, y equal to r sin theta. Therefore, x square plus y square equal to r square root 2 dx dy is changed to r dr d theta, where r varies from 1 to 2 and theta varies from 0 to 2 pi. Therefore, double integral 0 to 2 pi 1 to 2 r raised to 4 root 2 is constant, root 2 into r square into r for r raised to 5 sin square theta dr d theta. Now root 2 integral 0 to 2 pi integral with respect to r raised to 6 by 6 from 1 to 2 sin square theta d theta equal to square root of 2 divided by 6 integral 0 to 2 pi 2 raised to 6 minus 1 sin square theta d theta. Now next integration was with respect to theta for root 2 by root 6 2 raised to 6 minus 1 integral 0 to 2 pi sin square theta equal to 1 minus cos 2 theta by 2 d theta. That is root 2 by 6 2 raised to 6 minus 1 into 1 by 2 integral with respect to theta, theta minus sin 2 theta divided by 2 from 0 to 2 pi. Giving the limits, we get 2 raised to 6 minus 1 divided by 6 into root 2 into 2 pi. That is 3 equal to, the answer is 21 pi divided by square root of 2. So this is one application, evaluation of integral where the surface is taken on the xy plane, the projection is taken on the xy plane. Now we can discuss a problem not integrating up to, we can convert the integral to xy plane by taking the projection in the xy plane, yz plane and xz plane. Next question, convert the given surface integral. Convert the given surface integral into an iterated integrals by taking the projection of sigma on, first question, in the xy plane, second, in the xz plane, and third one in the yz plane. The integral is double integral over sigma xyz ds, where sigma is the portion of the plane 2x plus 3y plus 4z is equal to 12 in the first octant. We can identify the surface 2x plus 3y plus 4z is equal to 12. The given surface is 2x plus 3y plus 4z is equal to 12. If we divide by 12, x divided by 6 plus y divided by 4 plus z divided by 3 equal to 1. So this is the intercept form. That means the plane, the given plane, intersect the x-axis at the point 6, 0, 0, at the y-axis at 0, 4, 0, and at the z-axis at 0, 0, 3. Then the intersection of the plane in the first octant is given by this surface, whose base is the triangle OAB. The given surface sigma is the surface of the plane, that is the slanting plane on the surface, that is 2x plus 3y plus 2x plus 3y plus 4z is equal to 12. We can do this integration by taking the projection of the surface onto the xy plane, or taking projection to the xz plane, or we can take the projection to the yz plane. And we can convert this integral over sigma xyz ds using the formulas 1, 2 and 3. The formula 1 gives if the projection was taken to the xy plane. Before that, the given surface should be expressed in terms of z as a function of xy. Then double integral over sigma xyz ds will be double integral over r xy. Z should be expressed in terms of function of x and y into square root of, if z is given as function of xy, the square root of dou z by dou x whole square plus dou z by dou y whole square plus 1 dA. We can express z as a function of xy. First of all, from the given surface equation, 4z is equal to 12 minus 2x minus 3y. Then z is equal to 1 by 4 into 12 minus 2x minus 3y. And we are taking the projection of the surface onto the xy plane. That surface is given by the triangle OAB. And we have to find the region of integration. So the orthogonal projection of sigma on the xy plane is denoted as r, where r can be defined as, this is x-axis, as x is varying from 0 to 6. The triangular region can be defined as 0 less than or equal to x less than or equal to 6. And if we consider a strip AB parallel to y-axis, so that this AB is sliding in the triangular region OAB, where A is lying on the x-axis, where y is equal to 0. And the line AB is the projection of the surface on the xy plane. On the xy plane, we have z is equal to 0. Therefore, equation of this line is 2x plus 3y is equal to 12. Or using intercept form, this line is intersecting the x-axis at 6, 0, 0 and y-axis at 0, 4, 0. This can be written as x divided by 6 plus y divided by 4 is equal to 1. Therefore, from this equation, the y coordinate B is lying on the line AB, where y coordinate is equal to y by 4 is equal to 1 minus x divided by 6, or y is equal to 4 into 1 minus x divided by 6. Therefore, the region of integration is as x varies from 0 to 6, y varies from the line OA to the line AB, where y is equal to 0 to y is equal to 4 into 1 minus x by 6. So, this is the region of integration. Now, we can evaluate this integral by substituting all these values in the integral. That is, integral over sigma xy z ds is equal to double integral over r, that r is given by x is varying from 0 to 6, y varies from 0 to 4 into 1 minus x by 6, xy into g of xy. G of xy is the surface is 2x plus 3y plus 4z is equal to 12. Therefore, z is equal to 1 by 4 into 12 minus 2x minus 3y. Therefore, xy z is equal to, that is g of xy is 1 by 4, 12 minus 2x minus 3y dA, square root of dou z by dou x whole square plus dou z by dou y whole square plus 1. That is square root of, since z is equal to 1 by 4, 12 minus 2x minus 3y, dou z by dou x is equal to minus 2 by 4, minus 2 by 4 whole square, that is 4 by 16 plus dou z by dou y is equal to minus 3 by 4, minus 3 by 4 whole square, that is 9 by 16 plus 1 dx dy. Now, we can integrate. dA is equal to dx dy. Now, we can integrate this result. Now, the same integration, if you are taking the orthogonal projection of the surface to the xz plane. The second problem was the projection was taken on the xz plane. Our surface is x-intercept at the surface is 2x plus 3y plus 4z is equal to 12, that is x divided by 6 plus y divided by 4 plus z divided by 3 is equal to 1. The x-intercept is at 6, 0, 0, y-intercept at 0, 4, 0 and z-intercept at 0, 0, 3. This is sigma. Sigma is 2x plus 3y plus 4z is equal to 12. If we are taking the orthogonal projection of the surface to the xz plane, the xz plane is this one. The orthogonal projection will be the triangle OAC, in which the region of integration can be defined as R. From O to A, x is varying from 0 to 6. In the xz plane, the next variation will be to z. If we consider in the triangle OAC, a strip AB parallel to z axis, A is lying on the x axis where z is equal to 0 and B is lying on the line where y coordinate is equal to 0. Since the projection was taken on the xz plane, y is equal to 0. So, this equation of line AC will be 2y plus 4z is equal to 12. Therefore, z is equal to 1 by 4 into 12 minus 2x. So, the region of integration will be 0 to 6. As x varies from 0 to 6, z varies from 0 to 1 by 4, 12 minus 2x. And from the surface equation, you can express, since we are taking the projection on the xz plane, 3y is equal to 12 minus 2x minus 4z. Using equation 2, y should be expressed as a function of x and z. For y is equal to 1 by 3 into 12 minus 2x minus 4z. Now consider the integral. Double integral over sigma xyz ds is equal to double integral over r, where r is defined as x varies from 0 to 6, z varies from 0 to 1 by 4, 12 minus 2x, where x into z into y is substituted as 1 by 3 into 12 minus 2x minus 4z dx square root of dou y by dou x whole square. Since y is expressed as function of x and z, formula is dou y by dou x whole square plus dou y by dou z whole square plus 1 dA. That is 1 by 3 double integral 0 to 6, 0 to 1 by 4, 12 minus 2x into xz 12 minus 2x minus 4z into square root of dou y by dou x. Dou y by dou x is equal to minus 2 by 3, dou y by dou x whole square 4 divided by 9 plus dou y by dou z is equal to minus 4 by 3, so 16 by 9 plus 1 dA, where since the projection was taken to the xz plane, dA is equal to dz dx. Order of integration is first with respect to z, then with respect to x. Similarly, the same expression can be converted into integral if we take the projection of the surface to the yz plane using the formula 3.